In this series of videos, we're going to be taking a more detailed look at how ions form, as well as how different types of compounds are formed by combining different types of ions with each other. As an introduction to this topic, we can take a look at this version of the periodic table, which organizes elements in the same order that they're found on the periodic table, just with their Lewis structures shown, so that we can see that all elements within the same group, remember that groups are vertical organizations of elements, and every group has the same number of valence electrons. Now, the most important distinction or literal dividing line that exists on the periodic table is the dividing line that we see. If we go to the right-hand side of the periodic table, we can see a zigzag line that separates the periodic table into two halves depending on what type of element we are looking at. And we can replicate this dividing line simply by reproducing the zigzag line like so. And those of you who remember your periodic table organization will remember that all of the elements on the left-hand side of this line are metals, and all of the elements on the right-hand side of this dividing line are the non-metals. And the reason for this distinction is fundamentally based on how elements on each side form ions. And with metals, particularly if we look at the metals from aluminum and rightward, we can see that all of these metals have fewer than 4 valence electrons in their valence shell. And this means, especially if we take a look at aluminum here, it's much easier for aluminum to lose 3 electrons than it is for it to gain 5 electrons. And likewise with magnesium, it's easier for it to lose 2 valence electrons than it is to gain 6. And that's the common feature that we see with pretty much all metals, is that losing electrons is generally easier than gaining electrons. Whereas with nonmetals, particularly if we look at carbon and silicon and to the right, we can see that all elements to the right of carbon and silicon have greater than 4 valence electrons, or more than 4 valence electrons. So if we take a look at oxygen, which is a good example, it's much easier for oxygen to gain 2 electrons than it is for oxygen to lose 6. Or for chlorine, it's easier for chlorine to gain 1 than it is to lose 7. And the consequence that we see is that for the most part, nonmetals preferentially gain electrons rather than losing electrons. And as a quick review of terminology about why the number 8 is significant, the number 8 usually refers to the most significant number when it comes to the valence shell, which is the outermost shell of electrons, which is the only shell that is shown in Lewis structures. And ions form when the valence shell is full, which for pretty much every element that we see here, this means that when every element has 8 electrons in its outer shell, its valence shell is now full, which is why we also refer to this as the octet rule. Now, this is not true of some elements. For example, with hydrogen and helium that only have electrons in the first shell, remember that the maximum number of electrons in the first shell is 2, but the principle remains the same. Ions form when an element has a full outer shell. It's just for most elements on the periodic table, this number is going to be 8. And we can see that this is the case when we look at specific families of elements. So for example, if we take a look at the first family of elements on the left-hand side, what we call the alkali metals, which are lithium, sodium, potassium, rubidium, cesium, and francium below, all of these only have 1 valence electron. Now remember, the goal is to get to 8, but remember, an element can either lose electrons or gain electrons in order to get to a full octet. And for all of the alkali metals, obviously losing 1 electron is easier than gaining 7. And when we lose 1 electron, we are subtracting a charge of -1, which in terms of integer math is the same thing as adding 1, and that's why all of the alkali metals are going to have a charge of +1. Now, if we move over to the second family of elements, what we call the alkaline earth metals, which pretty much behave very similarly to alkali metals, only instead of having 1 valence electron, all of these now have 2. But the principle remains the same. It's much easier for the alkaline earth metals to lose 2 electrons than it is to gain 6, and when we subtract 2 electrons, that's the same as removing a -2 charge, and when we subtract the negative number, this is the same thing as adding a positive number, which is why all of the alkaline earth metals form a charge of +2 when they become ions, and so on. Now, if we continue this pattern over to the nonmetals, we can take a look at one of the most, if not the most, reactive family of nonmetals, what we call the halogens. These are fluorine, chlorine, bromine, and iodine. And we can see that all of the halogens have 7 electrons in their valence shell, meaning that they only need to gain 1 electron in order to have a full valence shell, which is much easier for them to do than losing 7. And when we add a charge of -1, adding a negative number is the same thing as subtracting in terms of integer math, and therefore we can say that all of the halogens form a charge of -1 when they form ions. Now, in the last review video, in the review series, we looked at 2 groups of elements, the carbon group and the noble gases, which is the family of elements that we find on the far right of the periodic table. And the noble gases are probably the most well-known example of elements that don't form ions at all, because noble gases already have a full valence shell. We can see that helium has 2 electrons in the first shell, and all of the elements below helium have 8 electrons in their outermost shell. This means that the noble gases don't need to gain or lose electrons at all. Now, the most important number on the periodic table that can help you identify the number of valence electrons, and therefore whether it's easier for an element to lose electrons or gain electrons, is the group number. For example, we can see the alkali metals are group 1A. This means that they all have 1 valence electron. The alkaline earth metals are group 2A. This means that they have 2 valence electrons. The noble gases are group 8A, which means they have 8 valence electrons, and so on. This is why, even though this periodic table is helpful because it already shows the Lewis structures, you don't actually need it, because all that you need to do is look at the group number in order to identify the number of valence electrons that each element has, depending on what group it's in. And at least it applies to these 8 groups here. To test your knowledge of identifying whether an element loses electrons or gains electrons more easily, depending on its position on the periodic table, you can take a look at the practice table below. So your goal here, number 1, is to be able to find all of these elements on the periodic table, identify what group they are in order to identify the number of valence electrons that they have, identify whether the element loses electrons or gains electrons, and of course how many, in order to determine what kind of charge the element will have as an ion. And once you've completed this, you can move on to the next video where we look at where electrons go when they are lost, or where electrons come from when they are gained, in order to understand how ionic compounds form.